Module 1, Part 3, Functions, Covariation, and Calculus Triangles. Covariation. For context, we're going to look at a 100-yard return for a touchdown in August of 2025.
And this ball's coming out. There's your speed depth. There it goes. Oh, there it goes.
Your task is to create a graph of the distance from the starting goal line as a function of the elapsed time. For context, the starting goal line is where the runner was standing before he took off with the football. Stop the video and complete the learning task before continuing. You may want to watch the touchdown video repeatedly to do the learning task. I start off by defining the variables. Let D be the distance from the starting goal line in yards, and T be the elapsed time in seconds. I create the graph with T, elapsed time in seconds, on the horizontal axis, and D, the distance from the starting goal line in yards, on the vertical axis. We know he starts at 0, 0, and when he's done, 12 seconds later, he's already at he's traveled 100 yards. From the times in the video, we know that he travels about 10 yards per second for most of the run, but for part of the run, in two different places, it takes him 2 seconds to go the 10 yards. So the graph reflects that. Our next task is to create a graph of the elapsed time as a function of the distance from the ending goal line. Pause the video and complete the learning task before continuing. You may want to rewind this video and watch the runner multiple times. Let D be the distance from the ending goal line in yards, and T be the elapsed time in seconds. We label the horizontal axis as distance from the ending goal line and the vertical axis as elapsed time. We know that when he's 100 yards away from the ending goal line, the time is 0, and we plot that point. As the distance to the goal line becomes smaller, from 100 to 90 to 80 and so forth, the time progresses up to 12 seconds when he crosses the ending goal line. Create a graph of the distance from the ending goal line as a function of the distance from the starting goal line. Pause the video and complete the learning task before continuing. We start by defining our variables. Let D be the distance from the ending goal line in yards, and S be the distance from the starting goal line in yards. We label our axes with the variables to make sure we have a clear understanding. Now, when we're 0 yards away from the starting goal line, we know we're 100 yards away from the ending goal line. For each 10 yards we move towards the ending goal line, we move away from the starting goal line. This results in the linear graph that we see. We will now move to another engaging context. This is an excerpt from a bike on a half-pipe video produced by Trey Wiley 6. Create a graph of the horizontal distance from the starting point as a function of the elapsed time. The elapsed time for this video is just over 10 seconds. For modeling purposes, assume the height of the half pipe is 12 feet and that the width of the half pipe from rim to rim is 40 feet. Pause the video and complete the learning task before continuing. We start by defining our variables. We let D be the horizontal distance from the starting point in feet, and T be the elapsed time in seconds. We label our axes appropriately. The horizontal axis represents the elapsed time in seconds, and the vertical axis represents the horizontal distance from the starting point. We know the furthest horizontal distance is 40 feet, and so you see that the maximum this graph reaches is 40. The closest that they can be is 0 feet from the starting point. This video shows going up and back to the maximum distance twice, which is what we've got here. Early on in the elapsed time, from like 0 to 1, the horizontal distance is not increasing as rapidly as in other areas because we're experiencing both horizontal and vertical change at the same time. But once that hits the bottom of that platform, of that half pipe, it's all horizontal distance, and that's why we see a more rapid change in that horizontal distance. For the next task, we will create a graph of the vertical distance above the ground as a function of the elapsed time. Again, the elapsed time for the video is 10.07 seconds. For modeling purposes, assume the height of the half pipe is 12 feet and the width of the half pipe from rim to rim is 40 feet. Pause the video and complete the learning task before continuing. We begin by defining our variables. Let d be the vertical distance above the ground in feet and t be the elapsed time in seconds. We know that at the beginning, the biker is 12 feet above the ground, goes down rapidly, that vertical distance drops, and then it's flat on that middle section, which we see here is down at 0, and then back up and down, back up and down. So with those flat spots where the vertical distance is not changing. For the next context, we have water flowing into a bottle at a constant rate. Your learning task is to graph the water height as a function of its volume. Pause the video and complete the learning task before continuing. Because the water is flowing at a constant rate, the volume of water in the bottle is increasing by a constant amount each second. We can think of the bottle as a group of stacked cylinders of various diameters and heights. Each cylinder must contain an equal volume of water. If the cylinder has a larger diameter, the height of the water will be smaller. If the cylinder has a smaller diameter, the height of the water will necessarily be larger. The way I set up this problem is I let V represent the percent of the filled volume. So when the bottle is completely full, it's 100%. When the bottle is completely empty, it's 0%. Likewise, the percent of the filled height. When it's full, it'll be at 100%, or when it's empty, it'll be at 0%. I plot these 2 points as visual markers, 0, 0, representing that the bottle is empty with 0% of the filled volume and 0% of the filled height, and also 100, 100, meaning that it's full in terms of volume and of the filled height. I considered each 10% increase in the filled volume. The amount of the increase in height will be greatest where the bottle is narrow, and least where the bottle is wide. Think about the cylinders. The shown graph models this behavior. For example, between 50 and 60%, we have a very small change in height. That's because the bottle is so wide there. In contrast, when we're between 90 and 100% of the volume, we see the largest change in height because the bottle is very narrow there. In your notes for your future forgetful self, identify the pain points for representing real-world phenomena graphically. Identify strategies to address those pain points. Pause the video and complete the learning reflection before continuing.